Swayam Prabha. Digital India. Educated India.
Welcome to this third lecture of module 12 of this NPTEL online certification course of environmental soil chemistry. In this week we are talking about different analytical techniques for measurement of pollutants in the soil. So, in the previous two lectures we have covered some instruments and some analytical techniques for measurement of inorganic and total nitrogen. And also we have started with the determination of inorganic phosphorus. For determination of inorganic phosphorus, we have discussed the Mehlich extractant, and we started with discussion of the ICP-AES or inductively coupled plasma atomic emission spectrometry, and now we are going to discuss the principle and other important aspects of ICP-AES. So, the principle of ICP-AES basically depends on some excited electrons. Now, the excited electrons, I mean when we excite the electrons of an compound or an element by some external sources. In this case, this is basically argon plasma. So, these excited electrons emit energy at a given wavelength as they return to their ground state after excitation by high temperature argon plasma. So, what happens when we energize the electrons of a compound by the high temperature of argon plasma? The electrons basically goes to the higher orbitals or excited states, and when they come back to the ground state after excitation, they emit some energy at given wavelengths. Now, the fundamental characteristics of this process is that each element emits energy at specific wavelengths particular to its atomic character. So, the wavelength at which these elements emits the light is very much wavelength specific. So, and also depends on its atomic character. So, the energy transfer for electrons when they fall back to the ground state, when they fall back to the ground state is unique to each element as it depends upon the electronic configuration of the orbital. And the energy transfer is inversely proportional to the wavelength of electromagnetic radiation. So, the energy transfer is less if the wavelength is high and vice versa. So, this is basically the principle of the ICP-AES on which it works. Now, we all know that the excited electrons, when they move back to their ground state, they emit some energy at specific, and this energy emission goes at a particular wavelength of light. Now, we all know this equation, that is E equal to hc by lambda, where h is the Planck's constant and c is the velocity of light and lambda is the wavelength. So, the wavelength of light emitted is also unique, and this is the principle of working for ICP-AES. Okay. Now, although each element, it is very important to remember that each element emits energy at multiple wavelengths. In the ICP-AES technique, it is most common to select a single wavelength or a very few of wavelengths for a given element. Now, the intensity of the energy emitted at the chosen wavelength. For example, we have selected a specific wavelength or a group of wavelengths. So, we measure the intensity of the energy that is emitted when the excited electrons come back to their ground state. So, when the excited electron comes back to their ground state, they emit the energy, and the intensity of the energy emitted at the chosen wavelength is proportional to the amount of or the concentration of that element in the sample being analyzed. So, depending on the concentration, the intensity of the energy emitted will be also vary. So, if there is a high concentration of that particular element in that sample, then the intensity of the energy emitted will be higher. So, thus by determining which wavelength are emitted by a sample and by determining their intensities, the analyst can quantitatively and qualitatively find the elements from the given sample relative to a reference standard. So, when we measure a reference standard and when we see the particular wavelengths at which we are getting the emitted energies and also their intensities, we can measure which element is present and what is their concentration. So, this is basically the principle of ICP AES. This is a very sophisticated technique and this is also very precise, dynamic and very accurate technique. Now, the wavelengths used in atomic emission spectrometry or these ICP AES ranges from the upper part of the vacuum ultraviolet, that is 160 nanometer, to the limit of visible light, which is around 800 nanometer in the total electromagnetic spectrum. Now, as borosilicate glass absorb light below 310 nanometer and oxygen in air absorb light below 200 nanometer, optical lenses and prisms are generally fabricated from quartz gas and optical parts are evacuated or filled by non-absorbing gas such as argon, because if there is a presence of oxygen, there will be absorption of light. So, that is why they are either evacuated or filled by non-absorbing gas like argon. So, this is a picture of these ICP AES instrument, as you can see, and this ICP AES instrument is also very costly instrument and it is a standard gold method for measurement of different elements. And these instruments you can see in all the standard environmental soil chemistry or soil chemistry laboratory or soil fertility laboratories. There is another variant of ICP, that is called ICP MS, and we will discuss this ICP MS in the later course of this module. So, this is the picture of ICP AES. Now, why it is called ICP? Why it is called inductively coupled plasma? So, to understand the reason behind this name, we have to see the schematic diagram of ICP plasma torch and how it operates. So, this picture basically shows this this diagram of these ICP plasma torch, and as you can see here, there are this consists of 3 concentric quartz tubes surrounded at the top by a radio frequency induction coil. So, here you can see there are 3 concentric quartz tubes. Okay. At the middle there is a sample, this is basically a capillary injection tube, and after that there is a plasma tube, and at the outermost there is a coolant tube. Okay. So, there are 3 concentric quartz tubes surrounded at the top by a radio frequency induction coil. So, this is the radio frequency induction coils. The sample is mixed with a stream of argon. So, the sample is being basically injected through mixed with a stream of argon using a nebulizer. You remember we have talked about the nebulizer in the construction of this ICP. So, basically these are the sample is mixed with the stream of argon, because it is inert in nature, using a nebulizer, and then carried to the plasma. So, this is the plasma, as you can see here, carried to the plasma through the torch central capillary tube. So, this white is a central capillary tube, as you can see. So, this sample aerosol is basically injected towards this plasma by this capillary injection tube, and plasma formation is basically initiated by spark from a Tesla coil. Now, an alternative radio frequency current in the induction coils creates a fluctuating magnetic field. So, you can see they are the radio frequency induction coils. This is the radio frequency induction coils. So, an alternative radio frequency is initiated by alternative radio frequency current in this induction coil is generated, which creates a fluctuating magnetic field that induces the argon ions and the electrons to move in a circular path. So, there will be a circular path of motion of these argon gases and also the electrons, and when there is a movement of these argon gas, so as a result there will be collision with the abundant ionized gas, give rise to resistive heating. So, what happens? There is a Tesla coil. So, plasma formation is initiated. You can see that argon is injected in this plasma tube, and this plasma formation is initiated by a Tesla coil, and an alternative radio frequency is generated, radio frequency current is generated in this radio frequency induction coil, which induces these argon ions which are produced in this argon ions which are present in this plasma tube, basically to rotate with the electrons, and as a result of this rotation there is a resulting collision with the abundant ionized gas, which gives rise to the resistive heating, providing temperature as high as 10,000 Kelvin at the base of the plasma. As you can see here, at the base of the plasma, the 10,000 Kelvin temperature is there, and between 6,000 to 8,000 also you can see at height of 15 to 20 millimeter above the coil, where emission is usually measured. So, basically this high temperature is helping these the sample or the element which are present in this aerosol to completely energized and completely ionized. This is the reason that this high temperature plasma is being generated. Again, there are 3 concentric rings, and in this concentrating ring, the innermost ring basically is the capillary injection tube, which basically generates the sample aerosol mixed with argon gas, and also there is another concentrating ring where the plasma where the argon is flow tangentially, and also there is a coolant tube. So, basically the so the argon is introduced to create the plasma. The plasma is being created by igniting it with the Tesla coil and creating a circular flow of this argon by inducing a current radio frequency current in the radio frequency coil, and there is a resistive collision with the unionized gas, creating a high temperature, and this plasma and this high temperature helps in the complete evaporation or complete complete dissociation of the elements which are present in the aerosol. So, at this high temperature, the outer quartz tube must be thermally isolated from the plasma, and this is accomplished by a tangential flow of argon shown in the, as you can see in this schematic diagram. So, this is how this the ICP plasma torch basically works. Now, passing the argon gas through this magnetic coil and then applying a spark sets the basically creates the plasma by atomizing the population of the argon molecules. Now, these charged molecules then have an inelastic collision. I told you there is a resistive collision. So, basically there is an inelastic collisions with the neutral argon that propagates to the plasma torch, which depends on the generation of the high frequency electric current produced by the electromagnetic induction known as the inductive coupling. So, that is why it is known as inductively coupled plasma. This plasma is generated by inductive coupling. Now, the torch will remain light as long as the magnetic field is present to encourage the movement of the atomized particles of the argon. As soon as it is switched off, the torch will not be working anymore. The sample is then introduced in an aerosol via nebulizer. The much higher temperature of the torch in the ICP leads to the atomization of essentially all sample molecules. So, a complete atomization of the all sample molecules, it is required that you create a very high temperature that can be only created by the production of the plasma. And for creating that plasma, you require inductive coupling, and for that inductive coupling you require these radio frequency coils. So, this is how this plasma torch basically works, and this is how this is the this is the central working principle of this ICP AES. Now, once this plasma torch has atomized the samples, the molecules are in excited states, and a detector then measure the light emitted by the sample as it returns to ground state to determine which elements are present. Now, compared to atomic absorption spectrometry, we will discuss this technique later on. Now, compared to this AES technique, these ICP OES or ICP AES, we generally use these two names very interchangeably, ICP atomic emission spectrometry or ICP optical emission spectrometry. So, ICP OES is able to quickly detect many elements, around 60 elements per minute, and the instruments detector determines this rate. ICP OES or ICP AES also features a much larger dynamic range than AES, meaning that less sample manipulation is necessary. And the biggest discrepancy comparing the ICP OES and other like AES is the higher price associated with the procurement of ICP AES. ICP AES is very costly instrument as compared to all other instruments. So, we have discussed the ICP AES. The second important thing for measurement of inorganic phosphorus is known as spectrophotometer. And sometime you will see people are using a term called colorimeter also. So, what is the difference we will see. Now, before measuring the concentration of orthophosphates or inorganic phosphate in spectrophotometer, we need to extract the phosphorus. So, for extracting the phosphorus, we need to have some kind of extracting solutions. So, there are two types of extracting solution we generally use. One is called Bray and Kurtz number 1 method, which is required for acidic to near neutral soils, and these extractant basically composed of 0.03 normal ammonium fluoride in 0.025 normal HCl at pH 3.5, and the other method is known as Olsen methods, and this method is required for neutral alkaline and calcareous soil, and these extractant Olsen extractant is basically 0.5 molar sodium bicarbonate. Now, spectrophotometry is a scientific method. You can see here the is a picture of spectrophotometer. So, the spectrophotometry is a scientific method based on the absorption of light by a substance and takes advantage of two laws of light absorption, and these laws are known as Beer's and Lambert's law. We will discuss them. Now, remember that this is the total electromagnetic spectrum, and based on that which portion, this is a electromagnetic spectrum which starts with the ultraviolet rays and then visible light, near infrared rays. So, basically which portion of the light is being utilized by this spectrophotometer gives the name of this spectrophotometer. If the spectrophotometer is using only visible light, then it is called visible spectrophotometer. If it is using UV plus visible portion of the electromagnetic spectrum, it is known as UVV spectrophotometer, and so on so forth. So, let us first discuss these two techniques called Beers and Lambert's law, but before going to Beers and Lambert's law, I want to discuss what is the difference between a colorimeter and spectrophotometer. You will see that these two terms are very much used alternatively by the soil scientists while they discuss about the inorganic phosphorus measurement. However, there are some differences. What is the differences? So, a colorimeter is generally any tool that characterize color samples. Num colorimeter comes from the color. So, basically they characterize color samples to provide an objective measure of color characteristics. So, in chemistry the colorimeter is an apparatus that allows the absorbance of a solution of a particular frequency or color of visual light. So, this is very important. So, at a particular frequency of visible light, it measures the absorbance by a solution. This is basically the utility of colorimeter. So, colorimetry makes it possible to ascertain the concentration of a known solute since it is proportional to the absorbance. So, colorimetry deals with the color of the solution, it basically deals with the specific frequency of the visible light, and it measures the absorbance by a solution, and by measuring the absorbance it measures the concentration of a particular solution. Now, a spectrophotometer on the other hand, it is a photometer which is a device for measuring light intensity. So, a spectrophotometer basically measures the light intensity and also it measures the intensity as a function of the color or more specifically the wavelength of light. There are many kinds of spectrophotometers, as I have already told you in the previous slide. Among the most important distinction used to classify them are the wavelengths they work with, just like UV vis spectrophotometer, visible spectrophotometer and so on and so forth, and the sources of intensity variation they are designed to measure, and these are some important considerations. So, other important features of spectrophotometers includes the spectral bandwidth and linear range. So, the most common application of spectrophotometer is the measurement of light absorption. Basically, we generally measure the light absorption by spectrophotometer. Now, the basics of spectrophotometry says that instruments allow light to pass through a cuvette. So, cuvette is a specialized container which contains the samples. So, the instrument basically allows light to pass through this cuvette containing the sample which absorbs some of the incoming beam. So, if there is an incoming light, incident light, and then we are using monochromator to convert them to a monochromatic light, when the monochromatic light passes through a sample in the cuvette, some amount is absorbed and some amount will be transmitted. So, when a ray of light of a given wavelength of an intensity, suppose it is the wavelength of the intensity I0, it is the incident ray, comes into contact with the perpendicularly with the solution of a tinted chemical compound, the compound will absorb part of the light radiation which is denoted by IA, and the remaining light, that is IB, will pass through the solution and strike the detector at the other end. So, if we combine IA plus IB, that will sum up to the incident wavelength intensity, and D is basically the path length. So, this is the basic. So, the following equation, considering all these things, the following equation can be demonstrated where I0 equal to IA plus IB. I0 is the total, where IA is the absorbed intensity and IB is the transmitted intensity. So, absorbance of light is related to the number of molecules present in the solution, that is, in other words, concentration of the solution. So, the Beer-Lambert's law defines the relationship. So, I told you that these Beer's and Lambert's law are the basic laws which governs the spectrophotometry. Now, this Beer-Lambert's law defines the relationship between the concentration of a solution and the amount of light absorbed by the solution. So, the basic form of this Beer-Lambert law equal to A equal to this eta dc, where A is the absorbance, we know that this eta is basically the molar absorptivity, and d is the path length of the cuvette containing the sample in centimeter, and c is the concentration of the compound in the solution. So, you can see that this absorbance is basically the multiplication of molar absorptivity, path length, and also the concentration in the compound in the solution. So, this is the basic forms of this Beer-Lambert's law. So, what is Beer-Lambert's law? In simplified form, Lambert's law says absorbance and path length are directly proportional to each other, and Beer's law says concentration and absorbance are directly proportional to each other. If we just consider this, obviously this absorbance and path length are proportional to each other, and absorbance and concentration are also proportional to each other. So, these are basically two laws, and we are combining them together to combine Beer-Lambert's law. So, in terms of intensity, this Beer-Lambert's law equation can be followed, where I is the intensity and I0 is the initial intensity, and E exponential mu is the basically coefficient of absorption, and x is the depth in meter. Okay. So, Beer-Lambert's law equation can be expressed in terms of this form also. Okay. So, the Beer-Lambert's law states that the quantity of the light absorbed by a substance dissolved in a fully transmitting solvent is directly proportional to the concentration of the substance and the path length of the light through the solution, which we have discussed just right now. Now, because Beer's law states this, it means we can both calculate the concentration of the solution by using these absorbance, or plot a graph of various concentration, align them to their correct absorbances, and use the colorimeter to find the concentration of an unknown solution. So, by using this relationship, if we make this, so this is very important. We can see here the path length d is, when we are using the specific cuvette, the path length is basically fixed. So, this d is constant. So, basically the absorbance varies with the concentration of the solution. So, by measuring the intensity of the light, we can measure the concentration of the solution. So, this is how we utilize the Beer's and Lambert's law for measurement of a concentration of the solution. Now, we have talked about the analytical methods for inorganic phosphorus. So, analytical methods for total phosphorus, there are two most widely recommended procedures for determining the total phosphorus, or we call it PT, are sodium carbonate fusion method and the perchloric and digestion method. Now, other alkaline and acid digestion methods which use these different components can be also used for these purposes also, but the major two methods which we generally use are sodium carbonate fusion method and perchloric acid digestion method for measurement of total phosphorus. So, what about the organic phosphorus? Organic phosphorus is also very important. So, organic phosphorus is there are two methods for measurement of organic phosphorus. So, the first method, this is actually the first method and this is actually the second method. So, the first method and second method are known as the extraction or Mehta procedure, or second method is known as the ignition procedure. Now, one thing is clear, that both of these methods are not measuring directly the organic phosphorus, they are indirectly measuring the organic phosphorus. How? They are either measuring total phosphorus, inorganic phosphorus, and thereby subtracting them to get the organic forms of phosphorus, or they are measuring the organic phosphorus which are converted to the inorganic phosphorus. So, this extraction or Mehta procedure basically involves the use of various acids and base treatments and the subsequent determination of inorganic phosphorus and total phosphorus in the extractant. Whereas, this ignition method use either high, that is 550 degree centigrade, or low temperature, that is 250 degree centigrade, to oxidize soil organic phosphorus to inorganic phosphorus. However, in both the cases, they are not directly measuring the organic phosphorus, they are indirectly measuring the organic phosphorus by subtracting these inorganic phosphorus from the total phosphorus. Okay. All right. So, let us wrap up here. We have covered the inorganic nitrogen and organic, we have covered the inorganic nitrogen, we have also covered the total nitrogen, and now we have covered the phosphorus, both inorganic phosphorus and total phosphorus and organic phosphorate. In the third lecture, we will start with determination of different salts. What are the methods of determination of different salts and other trace elements? We will discuss them in details, and then we will be discussing different organic pollutants, how to measure different organic pollutants also in the subsequent lectures. So, friends, let us wrap up here. Please stay tuned, and let us meet in our next lecture, that is in the fourth lecture of week 12, to discuss in details about analytical techniques for determination of salts, and also with other trace elements and organic pollutants. Thank you very much.